All right, so it's about time. Welcome back to DSP. Right. Good afternoon. So today we are going to focus on this lecture of FIR design, okay, finite impulse response filters. And we also will use the low-pass filter as our example. Yeah. And just to also announcement that I have posted homework number 4. And homework number 4 will go with this lecture. Okay, so you will be using the MATLAB library for FIR design. So you will get an FIR filter, and you will use it to convolve your signal, a signal of your choice, and the result should be low pass. So we'll cover that in the second hour. Okay, but for the first hour, let's dig into this lecture. So we have started last time to talk about this outline. Windowing in time and convolution in frequency. This is kind of the take-home message. Okay, how do we read it? When we design the filter, we will be doing windowing in the time domain. That's when we design the filter. But after your design, when you are ready to use the filter, you use it by convolution. I mean, you will use it by convolution in time. For sure, that's what the filter is about. Impulse response, right? The linear time invariant system. When you design a system, you convolve your impulse response with the signal. So that's for sure. But what could be confusing, as I mentioned last time? We mentioned last time that it could be confusing when we design, it's actually convolution in frequency. What's happening is convolution in frequency. That's the way, by this concept, we can understand what's going on. What's the kind of a trade-off design criterion for creating a low-pass filter. So this is conceptually, we are going to apply windowing in time, then which results in, we call this convolution in frequency, and that's the way we need to understand how this filter is designed. So convolution will happen in the frequency domain as we proceed into this lecture. Okay. So that's the first first item that we want to study. And secondly, after that, we will talk about Gibbs phenomenon. Okay? And in here, we will be basically studying the case when we have a sequence of functions. The sequence functions are, F1, F2, F3, F4. Sequence of functions, where each F is a function, 是一个函数。函数序列 a sequence of functions, right? So we study the case that when a sequence of functions converges to a final function. It's possible that there are different definitions about what it really means for convergence. Some convergence is uniform, and some kind of convergence is not uniform. So this is an important concept from, shall we say, advanced calculus, 高等微积分里面. In there is an important concept about uniform convergence, which will be applied in our study of designing a filter. Okay? So, and the general keyword here is Gibbs phenomenon. And then Gibbs phenomenon in this context will be about ripples, the ripples in your filter design. And then, so we will study how to suppress the ripples, because the ripples is unwanted. You want the passband to be flat, right? But inevitably, 无可避免的, inevitably there will be ripples. So you need to suppress that, and we can do that by choosing a window wisely. Okay? 那再次重申，上课在这教室不要再吃东西啊！那谢谢啊。好，啊。All right. So the first thing first. The first step is to consider the ideal low-pass response. Okay? Ideal low-pass response, if the cutoff frequency is denoted as omega c right here, then we just go back to the time domain, you get this sinc function, which extends to the left and to the left and to the right infinitely. Right? So it's an infinitely long function, signal in time, and we know that this impulse response for the ideal low-pass filter with the cutoff frequency cannot be implemented because it's simply infinitely long, 无限长, so it cannot not be implemented. Therefore, a naive idea, 一个天真的想法, which actually works pretty well. Yeah. So a naive but actually okay method. Yeah, it's a naive but not a bad idea. is to just do a truncation, right? Take the middle part. If this g of n extends to the right to the left infinitely long, we take the middle part. Just take the middle part and keep the middle part and call it a filter. It's that simple. Take the middle part, call it a filter. So how do we take the middle part? Suppose that we want to truncate from minus n to n, big N. Yeah? So we'll just define H, our design, to be equal to the ideal response in between minus n and plus n, and then everywhere else we just disregard. We disregard all the other samples outside that region. Keep the inside, discard the outside. Okay, is that clear? Then we call it a filter. This can already be called a design, exclamation mark, 惊叹号. Yeah, I think it's naive, but it's a good design actually. So we will be, let's try to examine its performance. If we simply do this, keep the middle part, how good is it? Yeah. How about the ripple? How about the transition width? Right. So in the next slide, we'll take a look. So in the previous page, let's rewrite this action of truncation as multiplication. So we are going to multiply the ideal response, G, with a window function, W. And W is simply 1 in between plus and minus n, and 0 elsewhere. And W is 0 elsewhere. So by just multiplying our ideal response with the window, we get a truncated filter. Okay, we get a truncation. So it should be clear that this window has a length of 2n plus 1 with this definition. So far, so good? We multiply the ideal response with the window. And this window has a name also. This window is called the rectangular window because it's 矩形的方方正正. It's a rectangular window. That's the way we call it. And so then the next thing follows. Okay? So since we are multiplying two things in the time domain, sample by sample multiplication, so that results in circular or cyclic convolution. Circular or cyclic, 循环的或是cyclic or circular, if you will, circular convolution. So which basically means that the integral goes from minus pi to pi. And it's circular because we know that both G and W, the Fourier transform is periodic every 2 pi, right? It repeats, both spectrums repeat themselves every 2 pi, right? So you just need to take one period, let's say from minus pi to pi, doesn't really matter. Take full one circle, go around the circle, and then there's also a normalization factor. And this is the way I denote it, okay? So I would denote this expression by circular, by the convolution with a circle to emphasize that it's happening in the frequency domain. It's happening in the DTFT domain. Okay, so far so good. This is just a second kind of convolution theorem. I remember we have worked on it previously. 刚开学 so there might be a discussion session or was it homework? Where I asked you to show this circular convolution theorem. Okay, it's a duality situation. It's a dual situation, 对偶性的 of the convolution theorem that we are more familiar with. Now we are familiar with the convolution in time domain, multiplication in frequency domain. But now, since this is the action we are taking, we multiply the ideal response with the window. Therefore, the effect in the frequency domain should be that of a convolution in the frequency domain. So far, so good? So a few remarks to make. First of all, about the notation right here, I put omega inside. But if you are sensitive enough, you should be aware that throughout the semester, we've been using EJ omega, right? We've been saying that, okay, if there is a G of n in the time domain, then its Fourier transform, its DTFT, is denoted as big G of EJ omega. And there's a reason. The reason is so that we have a unified notation system with Z transform. Okay? But here, I just feel that like every time, if you need to write EJ omega every time, I'm too lazy for that. Okay? This is too busy. So let me suggest, if you agree, let's just, without confusion, we are going to denote this sloppily, in a sloppy manner, 比较随性一点啊，比较洒脱一点，比较爽一点。I don't know. Sloppy notation, we are going to just write it down as g omega, just to emphasize that this is the spectrum. This is a function of the frequency. Okay. So that's the first remark. We write omega here instead of h omega right here, omega right here, omega right here, and omega is right there. This one, if you will, should be e to the j parenthesis omega minus theta. Okay, so but we are just going to use a easier and sloppy, maybe more sloppy notation right here. So that's the first remark. And the second remark, both g and w are real valued. Note that. Okay, so what's going on here? So maybe it's always good to draw a picture of what's going on. So on one hand, we have the ideal response. That's our small g. Small g of n may have this envelope. Envelope looks like that, sinc function. And then we sample. It's a signal. It's actually a discrete time signal in time, which extend to the left, to the right, infinitely. So that's g of n. And we take the middle part, right? We take the middle part. But I want to emphasize that both, we take the middle part, let's say from minus n to n. And this is our rectangular window with all ones in the from minus n to n, and we have a length of 2n plus 1. Okay, but here I want to emphasize that both g and w are symmetric around time 0. This is in the time domain, right? This is symmetric around time 0, right? Both of them. So therefore, as a result, what will happen in the frequency domain? When we have an even function in time, that means their spectrum must be real valued, right? And that's great. Yeah. So far, note that both of them are even functions. Therefore, their spectrums are going to be real valued, which is great, which makes it easier for us to talk about convolution later. Okay? Real value. So this is one feature I want you to notice. And then next, then we can finally take a look of their Fourier transform. Okay, take a look of their Fourier transform. Now, so we are looking at kind of an illustration, 一种图示啊, an illustration of calculating the convolution, the circular convolution in the frequency domain. So what's going on here? Right here, this is frequency domain, first of all. Okay? Frequency domain, and we are designing an ideal low-pass filter, and this is the ideal low-pass response in the frequency domain, right? Pass band right here, okay? If you will, pass band in here, and stop band right there, okay? And the spectrum repeats themselves every 2 pi. So can we agree that this is a frequency domain? In the frequency domain, this is the ideal magnitude response, which is impossible to implement. So therefore, we multiply in the time domain, and then we need to study the Fourier transform of the rectangular window, which looks like this. Okay, and it also repeats itself every 2 pi. Okay, and in this particular plot, we shift W by big W. Okay, we shift big W by omega. Actually, we flip and shift. All right? Yeah. So far so good? Yeah. So actually, I think it's worthwhile. So, and the next plot is a result of convolution. Okay, the result of convolution. Let's jump to the sort of the final outcome. Okay, now you see this curve. That's the result of convolving the ideal response with the Fourier transform of the window in the frequency domain. The result looks like this, okay, for this particular example. Okay, and as you see that there is ripples. There's ripple in the pass band. There's ripple in the stop band also. Okay, so that's the result. So take a look. But in the meanwhile, I think it's worthwhile to just derive a closed form expression for the Fourier transform of that rectangular window. Let's derive a closed form expression for this. Okay, I think it is worth trying. Right. So what I'm going to do is to say we know that Wn is 1 between big N plus or minus big N, 0 elsewhere. So therefore, it's rather straightforward to derive the Fourier transform of small w. Okay, shall we try that? Let's work on this together. Okay, let's work on this together. So where do I put? So big W of omega. By definition, it's a DTFT, so we should sum up all n, which actually goes from minus n to plus n. 1 times e to the minus j omega n. That's the expression, the summation expression for DTFT. Okay, that's according to the definition, right? So far, so good? Yes? And the final result is that sign. I remember the final result should be this. Yeah, I memorized the result. But let me just write it down first, and then we'll try to reach there. Okay? That's the final result. But how do we reach there? How do we reach there? Any suggestion? So I suggest that actually this summation is a sum of a geometric sequence. So this is a sum of 等比级数, a geometric sequence, right? And the common ratio is e to the minus j omega, right? So we just apply the formula. This summation should be equal to 1 minus that common ratio. 一减掉公比分之什么? First term, 首项, right? First term. What's the first term? First term is e j omega big N. It seems to be, yeah. That's the first term, 首项, first term. Times what? Times 1 minus e to the minus j omega. How many terms in total do we have? Yeah, that's the question. How many terms in total do we have? 2n plus 1, yeah. Yeah, wish me good luck. Okay, looks like something like that. It's pretty straightforward. Yeah, just the formula we all learned from high school, right? We have a finite length geometric sequence, right? Which has a total of 2n plus 1 terms, and the common ratio is e to the minus j omega, and that's the first term. That's the first term. So let's try to work this out. So how do we work this out? So here we have. What do you say? Let's pull this out first, okay? And the top and the bottom should be pretty similar. At the bottom, we have 1 minus cosine, what? 1 minus cosine omega plus j sine omega. And on top, we have 1 minus cosine. Everything looks the same except that we have a factor of 2n plus 1 of omega, again plus j, sine of the same thing, 2n plus 1 plus omega. Okay? Yeah. And then let's go this here. Let's use the space right here. So we have ej omega big N, and on top at the bottom, let's use some trigonometry. 用一些三角定理. Let's use some trigonometric identity. 三角恒等式, trigonometric identity. How do we use it? 1 minus cosine. 1 minus cosine. What is 1 minus cosine? Is 2 sine squared of half of that angle, right? 半角公式嘛, 背角公式, whatever. So 1 minus cosine is 2 sine squared, half of that angle, 2n plus 1 omega. Okay? And then what is, and then similarly, plus j sine less than, we also have a factor of 2 and sine of an angle, cosine of an angle. Do you know what I mean, right? Using this identity. And that thing is this thing, the angle, okay? The same angle right there. Yeah. 背角公式啊 doubling the angle. This is a trigonometric identity about doubling the angle. 背角公式 And at the bottom, we have exactly the same idea. Okay, exactly the same idea. 2 sine now 1/2 square actually, and plus j 2 sine of this angle omega divided by 2 cosine omega divided by 2, right? Yeah. So finally, we have e j omega n, and we can extract sine what 2n plus 1 divided by 2 times omega, extract that, and the inside becomes sine of that plus j cosine, plus j cosine of that. So that's top. And at the bottom, we have 2 sine omega divided by 2 and sine omega divided by 2 plus j cosine omega divided by 2. Okay, yeah. The final thing is to notice that it turns out these, the 3 terms right here, I'm circling, these 3 terms exactly cancel each other. Which gives us this final expression. Is it clear? Yes. 这边好像是哎。Thank you for the suggestion, smart guy. Okay, yeah. Anyway, so this is but one way, maybe not the best way, not the optimal way. But sometimes you get stuck. You know, you start your derivation, you want to finish it. Okay, T key. So this is the kind of the T key from my side. I don't feel like I need to apologize. But thank you. Okay, saved my life. Okay, but anyway, so you see that's the final result we are getting. Okay, so let's make a plot. Sine of 2n plus 1 divided by 2 of omega divided by sine omega divided by 2. Okay. So when you plot it, you should be able to get. First of all, it's a periodic function. The periodic function, and when omega approaches 0. When omega approaches 0, we need to apply the L'Hopital rule, right? So when omega approaches 0, we know that actually we have the case of, we have 2 cases. When omega is 0, say the same thing anyway. So its Fourier transform is going to have this sine by sine, sine over sine notation when omega is not 0. And then when omega is 0, it approaches or is equal to simply to 2n plus 1. Omega equals to 0. Okay? Yeah. So later we will come back to this. We will study that. So everybody okay with this? This is the final result. Yeah? So if you make a plot right here, big W of omega equals to, let me simply say it equals to sine over sine, okay? Sine over sine. So when we make a plot, we can study, this is important. Yeah, this is important. We need to work on this in details, okay? It helps. it helps us understanding what's going on, the ripple and stuff. Okay, so first of all, let's try to find out where this function crosses zero. What's its zero crossing? Yeah, so note that here this function crosses zero a few times, right? So we need to find out the first zero crossing right here. Where is it? I want to find it out. Okay, so how do we find it out? The first zero crossing here is a frequency when 2m plus 1 divided by 2 omega equals to what? Equals to pi. That's the first zero crossing. Yeah? So therefore, omega equals to 2m plus 1, which is the length of the window, dividing 2 pi. Yeah, that's the first zero crossing. So that's an important result. Okay, so this is one of the key results I want to get today. Okay, the first zero crossing occurs at this frequency. The first zero crossing, and then it crosses zero every multiple of that. Okay, so and then it crosses zero every multiple of that. Yeah. So we have negative, positive, negative, positive. Yeah. Until, yeah, because n could be large. Okay. In general, we're talking about n equals to could be a few hundred even. Yeah. Seriously. So in general, n could be large, but in the end, it approaches pi. Okay. Yeah. So in the end, the Nyquist rate it should be pretty small right there. Yeah. Maybe something like that. So let me just copy the plot. So in this plot, okay, so that's negative right there. So I'll just plot something similar. Okay, so we have a kind of a tail region, 尾巴啦，有点像一个尾巴。The tail region contains many ripples. How about the main region? The main region, what's the height? What's the peak at omega equals to 0? As we already showed there, right? The peak in the middle. Now this is the frequency domain, okay? So at DC, the DC has a value of 2n plus 1. Okay, so that's the height of W of the Fourier transform of the window. At DC, it has this exactly it's so tall. So tall, so just draw a curve like that. And we know that in the negative frequency part, everything is just symmetric. So let me just draw approximately something like that. It's symmetric around frequency 0. Okay, and I think this is an important sketch that we all need to go through. 要做一遍. Yeah, I think this is important. Why is it important? Because yeah, I want to go to my next page. Yeah. So wait. So this is important because here, so let's finish this slide first. The general question is now think about this is in the context of designing a filter, and we're picking the middle part, right? Truncating everything else outside that region, right? So just intuitively, when we increase n, the approximation should be better. When we keep more and more samples in the middle, the performance ought to be better, right? It got to be better. It should be better, right? Right or wrong? Yes? No? Intuitively, it's correct. Yeah. So when you can afford the memory, try to increase n, right? It's kind of common sense, right? So I would say so, yeah. The performance should improve when we increase n, okay? But then, we need to, at this time, let's review generally what's the design criteria about low-pass filter. Okay? When we design a low-pass filter, we want the ideal to be maintaining a constant gain for the passband, and then we allow a transition, and then when we reach the edge of the stop band, we want the gain over there to be as small as possible. Okay? So the design design parameters we have passband tolerance delta p, stop band tolerance delta S, we want both of them to be small. Okay? So we're talking about the largest ripple right there. We want to suppress that. And another criteria, another desired property is want to make the transition narrow. Make it narrow. We want to, ideally, the passband right there, then we want to just all of a sudden reach the stop band with very short transition, very narrow transition. That's desired. 是符合理想的. Ideal response should be passband, no transition immediately stop band, right? That's ideal, but it's impossible, right? So now we're designing, we allow there to be a transition, but at the same time, we want it to be narrow. While suppressing, 要压抑它,压制它, while suppressing the biggest ripple. Okay? Yeah. So far, so good? Any comment on this? Can we agree that these are the two design goals? Two of the design goals. 设计的一个目标嘛, It turns out that, as we will learn today, kind of take-home message is that it turns out that these two goals, suppressing the delta while making this transition narrow, these two goals conflict each other. 它是有互相在对冲的. They're like, there's a trade-off. There's a trade-off. So which has something to do with my previous question. What was my question? What was my question? My question was, in the previous page, I want to ask, will the performance improve when we simply increase n? When we simply increase n, increase this n right here, yeah? When we increase n to include more and more samples, will the performance improve? The answer turns out to be yes and no. Yeah, yes and no. That's my answer. Okay? Yes and no. Yes, because from the basic Fourier transform property, to increase in time means to narrow in frequency, right? So really, the transition width will become narrower. That's for sure. When we increase n, that design goal can have a better performance in terms of the transition width. Okay, so that's the yes part. Yes part. Okay, but what is the no part? The no part is surprisingly, when we increase n, this largest ripple will not be suppressed. That might be the surprising part. Okay, transition can be made narrower and narrower, but nonetheless, nevertheless, it's a pity that the largest ripple will not be suppressed. It will remain so large, and this is called the Gibbs phenomenon. So in the next slide, I was planning to let's try to plot the frequency response as we increase n to see what really is going on. Okay, to see what really is going on. So first of all, maybe I can erase this. Can I erase the derivation? Can I erase the derivation? Okay. Now. Okay, so we want to study, so let's do this together. We plot the frequency response as we increase n. Okay? And the frequency response will be the design. Let's say our design is called h sub n denoting the length, right? The length on each side. And then it equals to 2 pi, 1 over 2 pi, integral minus pi 2 pi, w of is it omega minus theta and g of theta d theta, right? Yeah. So that's the expression, the circular convolution. Okay, and so we want to. I want to give you this exercise, and we want to plot the frequency response as we increase n. So, how do we start? Maybe let's go. So this page is left blank. Okay, so you can work on it on your own. Maybe we can take a few minutes. So let's take 2 minutes for you to just work on this. Try to work on it. what will happen when we increase n? So I want to see this. Yeah, please try to. This is for a pretty small n, I'm afraid. So this n looks like 1, 2, 3, 4, 5, 6. I don't know. 7, 8. It looks like a small n. Okay, but now when we increase n, what will happen in the frequency domain? We're talking about making a convolution of the ideal low-pass response to the Fourier transform, which changes as n increases. Okay? Shall we take like maybe 2 minutes? 好，大家可以如果愿意的话大家动手画画看啊。Yeah. So how do we convince ourselves that the transition width will be narrower while I claim, and I was telling you that the ripple, the largest ripple will not be suppressed. Will not be suppressed. So what's going on? Okay. Okay, so let's try to figure out together, right? Shall we? So first, I want you to again look at this plot on your left. Okay, it should be pretty clear that the Fourier transform sine over sine this function when n increases, what happens? When n increases, this main lobe, this main part in the middle is called the main lobe. By the way, the main lobe is going to become taller. This will become taller when n increases, right? So main lobe will become taller and thinner because the width is inversely proportional to n plus 1, right? So imagine that when n increase, we get taller but thinner. The height, the 高度, the height is proportional to n plus 1, but the width is inversely proportional to 2n plus 1, which is the length of the window in the time domain. Okay? So it should be pretty clear that this shape should grow taller but thinner when n increases. Okay? When n increases, That's a general trend for the Fourier transform of W. That should be pretty clear. Okay? Taller and thinner. One is proportional, the other is inversely proportional. So you kind of get the idea that the area in the middle is probably should be approximately staying the same as n increases because its height. If you imagine that this is approximately a triangle, right? The height is increasing, the width is inversely proportional. So the area. So we talk about the area, which will be important. This area should stay roughly the same. Okay, we'll come back to that. So, and that will be helpful when we talk about convolution. Why? Because convolution right here now if you look at on the right of this board, on your right-hand side, convolution is an integral, right? And an integral is about the area under a curve. And the area, of course, can go positive or negative. We know that, integral. Yeah. Calculate integral. So the convolution is about an integral within the range. We talk about the area under the curve. Right? Okay. So we are going to, so let me just rewrite this as theta minus omega. Doesn't matter, okay? Because W, big W is symmetric. Okay? Big W is symmetric. And yeah, so here what we really have is big W of theta. I'm sorry, this should be the theta axis. Theta minus omega. Okay, so when we omega is a parameter right here. So we are just evaluating this integral as a function of omega. So what does that mean? That means that W, big W, is shifting to the right, and we multiply it with G, which is ideal, very simple. 1 in the pass band, 0 in the stop band. And we're calculating the area under the curve after multiplication. Okay? So should we say that this is, by now it should be clear, because of G theta only goes from minus omega to the cutoff frequency to the plus cutoff frequency. Is that clear? Because G omega is 1 in the pass band, 0 elsewhere. Okay, so we can modify the boundary, the top and bottom. So we evaluate the, so seriously, what we're doing is going to evaluate this area. Okay, let's say from, if, yeah, I'm running out of space, but let's say if here, it's a long period, let's say here, that's the negative frequency part, okay? Yeah. So we are going to evaluate this integral now within this range, from minus omega color frequency to plus color frequency, okay? So we evaluate this area, but imagine, please imagine that this sine over sine function can move to the right. So, okay, so I use dash line, 我用虚线画的地方. So here, when we, please imagine this function is moving left, right, okay? And we are going to evaluate its area under the curve in this interval, within this interval, from minus to plus color frequency. So far, so good? Yeah. So what's going on? First of all, so now let me change to the green, okay? So first of all, let's say if omega is moving to the far right, let's say omega moves to the far right now. Far right, okay? So at a high omega, simply because the sinc function, sinc-like function, 长得像sinc, not exactly sinc-like function. The sinc-like function now, it doesn't overlap with the pass band. So when omega is large, the integral should be almost 0. Because now everything under the curve is like the tail part. This tail part barely has any area. 几乎没有面积嘛, barely has any area. So we know that if I allow to draw the frequency response far to the right should be nearly 0, and there should be ripple. Okay? And this will be an interesting case. Let's consider this case now. When omega is exactly the color frequency, what happens? When omega is exactly at the color frequency, the area is 1/2 of the total area. Can we agree? So that gives us this point. This point is exactly 1/2. Okay? Because we are looking at only half of the response. Only half of the response right here. We're looking at only half of the response. So this area is 1/2 of the total area. Can we agree on that? Yeah? This area is 1/2 of the total area. And that gives us exactly this point. Okay? And finally, when let's imagine now when omega is inside the passband, this main lobe, let's say when the main lobe is completely inside the passband, then the area should be large, right? Because the main lobe, the main part, the main positive part is inside the passband. Okay? And it turns out that the total area from minus pi to pi, the entire period, you can prove it, is 1. Okay? And the main lobe has an area of, I'll come back to this. The main lobe actually has an area 1 plus 2 delta. Yeah, it's slightly larger than 1. The main lobe is slightly larger than 1. Okay? So, the result, if we will, so it's already pretty busy, but hopefully I will be working on this. Yeah. So the resulting frequency response to jump to top, this is 1 plus 2 delta. That's a peak. No. It goes to 1/2 exactly at the cutoff frequency. But then near there should be a peak of 1 plus 2 delta. No, 1 plus delta. We'll come back to this. Turns out that the peak should be 1 plus delta, where delta has something to do with the main lobe area. If the main lobe area is 1 plus 2 delta, then the peak ripple right here will be 1 plus delta, whereas like everything will be symmetric here. In the stop band, it dropped to minus omega. And then there's ripple. So this is what I want to plot. The final plot should be, there will be ripple as we move the sinc function to the left or right and calculate the area. There will be ripple. And the largest ripple turns out to be 1 plus delta, where delta has something to do with the main lobe area. Okay? And this is minus delta. So that's already a busy plot, right? So you can try to understand this when you go home. But I do have a slide, okay? So I do have a slide showing this. So let's jump to this plot right here. I'm jumping a few slides ahead, okay? So in this slide, I summarize this for you, okay? Turns out that whenever we use a window to design a low-pass filter, and we talk about the frequency response, the peak ripple is denoted by 1 plus delta. And the most negative response, because of symmetry, should be delta, should be minus delta. And the middle, we have 1/2, exactly 1/2, no matter which window we use, okay? So, and it has something to do with, the reason is because we are moving this Fourier transform the window to the left and to the right and calculating the area. Calculating the area, the accumulated area until this frequency. 累积的面积 accumulated area until this frequency. That's the thing we are calculating. Okay? So when the entire main lobe moved inside the passband, that's when we reach the tallest peak. Okay? So when the entire main lobe moves inside the passband, we reach the tallest peak. Yeah? So that's what this plot is trying to show you. Okay? I argue that when the entire main lobe just moves inside, then that's where we get the tallest peak. Okay? So are you getting it? I wish I can. Let me seriously draw on this. Can I draw on this? When the entire main lobe move right here, okay? When the entire main lobe just move inside, I'm drawing a curve. Yeah. Yeah. When the entire main lobe just move inside the pass band, we get the tallest peak. So that is to say that actually this tallest peak occurs at frequency omega c minus the main lobe width, the half of the main lobe width. Okay, so this is a conclusion I want to pull before we take a break. Okay, so I want to just add one thing to this already pretty busy slide, that this width right here between the cutoff frequency and the largest peak, this is exactly equal to 1/2 of the main lobe width. Okay, 1/2 of the main lobe width. So if the main lobe width is called, what's my notation? The main lobe width is called omega m, okay, delta omega m. So this is exactly delta omega m divided by 2, where omega m denotes the width of that main lobe. Okay, let's take a break before we continue our discussion. Okay, oh, this is pretty bad. I'm damaging this. 关掉还可以，可能要擦一下这个。拜托拜托，好，幸好擦得掉。幸好还擦得掉。黑板先保留好了啊。
为什么 main lobe 的面积是1+2丢掉是定义的吗？
这个是我在准备的时候，我自己觉得我看出来的。对啊。
那 total area 等于是指什么东西 total area？ 是指
它那个这个东西啊，它整个如果你从负拍积分到拍，它那个 area 一定会等于1。这个会有个假设了啊，这个有个假设我没有讲，我们待会儿看的，比方说一些的 Windows 啊，全关掉。 All right. So a few points to clarify. A few points I want to clarify after discussion with some of you over the break. 下课时候讨论啊。So what are the things that we need to clarify? First of all, about this point passing 1/2. So I may need to be more careful. Okay, this might be just an approximation. When I say that the area, the half of the area, right? If the entire area is 1, okay, which you can show by basic Fourier transform property. If the entire area under curve, we talk about positive main lobe, negative side lobe, and then positive second side lobe, and so on. Main lobe, side lobe, okay, 有这种名字啊。Main lobe, side lobe, 旁边的 side main lobe, 主要的啊 main lobe, side lobe 啊 main lobe, side lobe, the entire area is 1. Or should I say it's actually 2 pi? The entire area, if you integrate big W for the entire period of 2 pi, you get, it turns out to be equal to 2 pi times W0 in the time domain. This is applying the formula for inverse Fourier transform. Going back from frequency to time, inverse Fourier transform tells you that the entire area is actually 2 pi. If W0 is 1, and is W0 1? Yes, for rectangular window, W0, actually W everywhere is 1, right? So the area is actually 2 pi, but then in cyclic convolution, there's a factor of 1 over 2 pi. So therefore, when I say the area is 1, I mean after normalization. After normalization, the area becomes 1. Okay, so I hope that this is my sloppy part. 我有点随便一点, but the area is actually 2 pi. But when after division by 2 pi, it becomes 1. Right? The entire area is 1. Let's say the entire area is 1 unit. Okay, it's 1. Then the left half and the right half should be each 1 over 2, 0.5. Right? 0.5, 0.5, I sum it up, it becomes 1, the area. So when I say that this point passes to 1/2, it depends on two things. First of all, the window has to be normalized. The window has to have a height of 1 at time 0. Okay? So that's first assumption. And the second assumption is that our main lobe width should be much smaller compared to the color frequency. Let me repeat that. Okay? The width of main lobe, this main lobe, should be much smaller than the cutoff frequency. So that means n needs to be sufficiently large. When n is sufficiently large, the entire main lobe becomes thin, right, and tall, right? And then we can, let's say if the color frequency is in your homework, if the color frequency is 0.33 pi, right? Then you want to make the main lobe much narrower than that. So when that happens, then the entire area, when we come back to this plot, the entire area of the left-hand half area, when the middle of the main lobe moved to the color frequency, now this area should be around 1/2, between minus color frequency and plus color frequency, okay? Approximately. If this width, this main lobe width is much narrower than the color frequency right there. Okay, 我把这收一下啊. Okay, so if the main lobe width, let's say it equals to, it approaches, is approximately 1/2 if the main lobe width is much smaller, much narrower than the cutoff frequency, then we can say that the approximation should be good. Okay? But otherwise, hopefully, we have shown that the peak there is always going to be 1 plus delta. And what is delta? What is delta? Delta has something to do with the main lobe width, the main lobe area. Okay? The main lobe area turns out is 1 plus 2 times delta. And what is delta? Delta is actually the summation. Delta is the summation of all the area right there. delta equals to the summation of all these areas when it extends far, far, far right there. Starting from right here, the edge of the main lobe, start from here to the right, if you take an integral, this area turns out to be negative, and let's call it minus delta. Okay? And because of symmetry, if this is minus delta, then on the left-hand side, this part, the area should also be minus delta. Minus delta here, right? But then we say the total area. What is the total area? Total area is 1. Therefore, this main lobe area is 1 plus. So main lobe area plus minus delta equals to 1. That's the entire area. Therefore, the main lobe area is 1 plus 2 delta. Yeah. Is that clear? So it's the main lobe area equals to from minus width to plus of half of the width. If you take the integral, that's the main lobe area should be equals to 1 plus 2 delta. Okay? Yeah. And this delta has something to do with that. Yeah. So it turns out that this delta never changes when we increase n. This delta does not change when we increase n. That's one thing to notice. Note that delta does not approach 0. Does not approach 0. As n approach infinity. So that's where the problem is. That's where the problem is. Okay? This delta doesn't approach 0 when n approaches infinity. So what does that mean? That means that this peak is always going to be 1 plus delta. It doesn't suppress as n. It doesn't go to. Delta does not approach 0 as n approach, as we increase and as we include more and more samples in our design. Doesn't help on delta. That does not help reducing delta. And that's an important concept. And this is an example of Gibbs phenomenon. Okay, Gibbs phenomenon. But nonetheless, how about the transition width? The transition width, strictly speaking, is slightly smaller than the main lobe width. Okay? And this requires some explanation. Okay? Let's take a look at this figure. Okay? Let's take a look at this figure together. The main lobe width, as we now know that the main lobe width is in between this point, the largest peak, and the most deepest ditch right there. Okay? The largest peak and the deepest valley right here, the distance right here, it will equal the main lobe width. Okay? Just by inspection. Now, if you understand the meaning of circular convolution, and a good approximation when n is sufficiently large, these 2 points is equal. The distance between these 2 points is exactly the main lobe width. Okay, yeah. First of all, but then let's be careful. Usually, when we talk about filter design spec, the transition width is not defined as the distance between this peak point and the valley point, but instead we define the transition width as this distance between 2 points, these 2 corner points. That's the transition width. So that's how the transition width is defined. Okay? And what are these 2 corner points? This is 1 minus delta. So 1 plus delta, 1 minus delta. Okay? 1 plus delta corresponds to the main lobe width, but 1 minus delta is, we define this to be the actual transition width. That's the transition width between this point and that point, between the 2 corner points. So this just by plotting, we understand. Now we understand, we see that the transition width, by definition, is always going to be slightly smaller, more narrow than the main lobe width of the window we use. Let me repeat that. This transition width is this width right here between this point and that point. Okay? Between the 2 corner points, that width is always going to be smaller, slightly smaller than the main lobe width. Why? Because here this response is monotonically decreasing, right? The response keeps dropping from 1 plus delta later to 1 minus delta. And it reaches plus delta right there at the edge. That's the definition of the edge of the stop end, right? And it keeps dropping to minus delta, right? That's why this region, the entire region is the main lobe width, whereas the region between when it takes to drop from 1 minus delta to delta, this region is narrower. And that's actually this region, more narrow region is the definition for transition. Transition width is defined by that, okay, by 1 minus delta and plus delta. Okay, do we see that? Yeah. So the main lobe width right here, main lobe width versus transition width. And note that 1 plus 2 delta equals to the main lobe area right here. Okay, that's 1 plus 2 delta. And the total area is 1. Okay. After normalization by 2 pi. Yeah. All right, so with that, now you can imagine when we increase n, the transition width being narrower than the main lobe width. Now, what is the main lobe width? When main lobe width is inversely proportional to n, right? So it's rather easy to explain that when n increases, what happens to the transition width? When n increases, the main lobe width decreases. Therefore, the transition width decreases inverse proportionally. 会成反比了，基本上啊。Basically, it will be inversely proportional to the main to n, or to n plus 1 to be exact. That clear? So finally, let's make another plot. Now we can talk about as n increases. Let's blow up this part, okay? So suppose that this is our ideal response, pass band, stop band, and at a smaller n, we have a fine approximation to the ideal response. This is the frequency domain. There's going to be 1 plus delta, there's a peak, and 1/2 right here. So that's 1 n, okay? And as n increases near the edge, we see that now, as n increases, let me use another color. As n increases, we should still get a peak. It's just closer, still the same peak of 1 plus delta. Okay, same peak right there. But now the transition becomes narrower. And it just undershoot to minus delta right there. And then going up. Okay. So that's what's going to happen. We still have this tiny, but just non-zero peak, deviation from the ideal. That's over there. Something like that when we increase n. Yeah. So that finished I try my best to plot this by hand. Okay. Yeah. When n increases, you see the transition becomes narrower. But yet the largest ripple is not reduced. So that gives us to kind of some insight what's going on. This is an example of what we call non-uniform convergence. Okay. Any question right here? Can we imagine what happens to the frequency domain when n increases? Any question? Any comment right here? That little thing right there is always going to be there. This overshoot, undershoot is always going to be there. It's just that they go really, really close to the color frequency, okay, when n increases. And when n increases, far away from the color frequency, the response approaches to unity. Okay? I'm saying that far enough away, the ripple is reduced, then here the response looks fine. But just as we go closer to the color frequency, there is always an overshoot of delta. And the size is not reduced by increasing n. And so in the next few minutes, I would like to talk about what this means mathematically. Okay? This is a perfect example of what we call the Gibbs phenomenon. Okay, so this is the next topic. I want to introduce to you the Gibbs phenomenon. So let's try to see what's going on. These are a few mathematical facts if you are more mathematically inclined. 如果你比较喜欢数学的话啊。So for pondering purpose, when I say that this overshoot is not going to be reduced, we say that the maximum approximation error, that's overshoot, right? If we take the entire omega and consider the maximum approximation error, that's the ideal response. This is the result of our design, right? This maximum deviation, maximum approximation error is not, we cannot decrease it by increasing n. And this is called the Gibbs phenomenon. Okay? What is it? So we need to understand, but notice one thing, that the limit of Hn approaches G everywhere. Is it true? Is it still true? That's a tricky question to answer. Is it still true that limit n approach infinity, if we evaluate our design at a frequency and compare that to G, I mean, is it still true that when n approaches infinity, the equality holds? Yes or no? Yes? Yes. No. No. Okay, so we have diverse opinions. My answer is yes. If you write it this way, but the tricky point is that they don't approach, the equality is not approached at the same speed. 它那个趋近的速度不相等嘛，So what are we talking about? So I said that point-wise, we consider individual omega, like say this omega, or that omega, or that omega, or that omega, or this omega. Okay, if we consider one individual omega, yes, the limit is approaching ideal. Okay, for every single omega. Okay, this is correct. Okay, this is correct. But the problem is when we come, but yet we're talking about the maximum approximation cannot be reduced by increasing n. So what's going on? These two concepts seem to be in conflict, right? Point-wise convergence, but globally the maximum approximation error is not reduced when we increase n. So there seems to be a conceptual conflict right here. 观念上有点冲突啊，有没有觉得啊？ Now are you feeling it? There is a conceptual conflict right here. Okay, but we can kind of mitigate. 可以减缓这样冲突啊。我们可以调节这样冲突。We can mitigate this conflict by a careful definition. And now here comes the definition. So I want to share with you what it means for a convergence to be uniform. 均匀收敛啊。So what's the definition? Definition is written right here. So let me read it first. We say that a sequence of functions denoted as f sub n, where n equals to 1, 2, 3 integer, right? A sequence of functions, is said to converge uniformly to a function g over an interval, some kind of interval I. So if then epsilon and delta thing comes in, right? If for any epsilon, positive epsilon, there exists an integer big M, such that everywhere the approximation error is smaller than epsilon, everywhere in I, as long as big N is greater than or equal to big M. That's the definition of uniform convergence. A sequence of function approaching G, converging to G uniformly if the important detail is that for any epsilon, there exists an m, an integer m. But this m is the same m for every x. That's a key detail to pay attention. Okay? That's a detail to pay attention. If for any epsilon, there is an integer m, and the m is the same m for every x in I, such that the approximation error absolute value is smaller than epsilon. So that's a definition of a uniform convergence. So are you feeling that this definition is stronger than the usual definition of convergence, of pointwise convergence? Is it stronger? Are you feeling it? I'm emphasizing that this got to be the same M, okay? Okay, so this is one point for you to ponder. There's a difference in definition, and this definition is stronger in that we talk about the same M for every x in the interval I. Okay, so back in our context, our interval is from minus pi to pi, okay? And our sequence of function is h sub n. In the frequency domain, that's the sequence of function we're talking about. Every time you choose an n, you have a result, right? So when the n increases, your result is a sequence of function. A sequence of functions, okay? Yeah. And which approaches the ideal response pointwise. If you talk about every omega, yeah, indeed, it approaches the ideal as long as you keep increasing n. Eventually, your response will converge to 1 for stop band and 0 at 1 for pass band and 0 for stop band. That convergence eventually will be true. Yeah. But it's just that, however, there is an overshoot. This convergence is not uniform. This convergence is pointwise, but not uniform. Okay? So I just introduced then what is the uniform convergence definition. This is the definition. I'm trying to share with you that pointwise convergence, but yet not uniform. This is a case of non-uniform convergence, okay, of a sequence of function to a target function. Okay. All right. So the fourth remark I want to make on this slide. Turns out that if you have taken advanced calculus from the math department, 高维啦，高维会教这个那个领域通常叫做分析啊，数学领域叫分析 analysis， and there's a real analysis, complex analysis， 实分析、负分析这些的啊，就是通常在搞那些 epsilon 跟 delta 的那类的叫做分析啊。In mathematical analysis, this is a well-known fact that a sequence of continuous functions cannot uniformly converge to a discontinuous function. That's a theorem. There's a theorem for you to be aware of. And how do we apply this concept? How do we apply this concept in our context? This is a theorem, okay? Any sequence of continuous functions, let's say if each of Hn is continuous, then the limit cannot converge to a discontinuous function uniformly. A sequence of continuous functions, when it converges to a final function, that function, if the convergence is uniform, then that final function also needs to be continuous. Okay? But now, applying this theorem, what we have is that each h is always continuous. But the target, is it continuous? The target is the ideal magnitude response, right? This target function, g of omega, has a discontinuity at the cutoff frequency. Okay? So the limit is discontinuous while each member in that sequence is continuous. Yes, convergence is still true, but the convergence will not be uniform. And this is a theorem, the direct consequence of a mathematical theorem. Okay? For those of you that are more inclined, please, you are highly encouraged to take advanced calculus before leaving NTHU. Okay? I highly recommend doing that. Okay? I did that at your age. 我大三的时候修的啊，反正数学系啊。 is a 讲到这，我来跟你们分享一个蛮有趣的。我讲中文好了。Does anybody don't not understand Chinese？ 其实有点可惜，我们国际生几乎大部分都那个，后来只剩1、2位啊。所以 let me say this in Chinese。你知道这个？我以前修高维的时候拿那个课本啊，我怎么学习的？我就是把证明遮住。然后就是他，因为数学系的课本有时候就定义定理证明啊，定义定理证明，然后就引理、corollary、lemma 这些到这定理啊，比较像你们线性代数的那感觉。我就把证明遮住，然后就开始自己推导看看了。背章前面已经 define 过定义，然后看看我推导的出来，推导不出来。如果推导出来的话，我的方法跟课本一不一样，有时候不一样，有时候课本通常写得更好啊，有时候通常写得更好。所以这是我学习的方式。后来那个有一次我看报纸，就讲到说中华民国啊，曾经有一位财政部长啊，叫做郭婉容，不知道大家有没有听过？很久以前的一位财政部长啊。后来找到一段他的访谈呢啊，大家可以去 search。这位是民国70、80年代啊的一位财政部长，叫做郭婉容。他先生叫倪文雅，是立法院院长。以前在那个早期还没有改选的时候，倪文雅这样，夫妻档啊，他是他的后来再娶的妻子啊，第二任妻子。这位财政部长，他当初他年轻的时候修高维，也是跟我一样啊。有段访谈讲到说，郭婉容在修高维的时候，也是把证明遮住，然后自己推导。后来他就当财政部长了，好吧？好，我就当清华大学教授啊。I highly recommend you to take advanced calculus before you leave NTH, because you might be the next 财政部长, okay, the Minister of Finance, okay, of Republic of China, okay, or Taiwan. All right, so now exercise time, right? So now let's try to describe what does it really mean for convergence to be non-uniform. Shall we try that? This is an exercise. How do we describe non-uniform convergence for a sequence of functions? And let's recall that I'm repeating the definition right here, same definition. Okay, so if the definition for uniform convergence goes like this, a sequence of functions converges uniformly to G over interval if, if that's the definition, okay? What follows if is the definition. If 后面就是定义了啊。If for any epsilon there exists an integer m such that the error is smaller than epsilon everywhere in I for any m bigger than or equal to big M. So that's a definition of uniform convergence. So now can I invite you to think about then what is the definition for non-uniform convergence? What's the opposite? What's the definition of a sequence of functions which converges but not uniformly to G? Anybody? How do you describe mathematically in this kind of language? Okay, in this kind of language. Let's take 2 minutes. Okay, we have time. 2分钟想一下啊。How would you describe non-uniform convergence? It needs to converge, but yet not uniformly. How do you describe that?好，来腾出一些空间啊。 So how do anybody how do 胡定芳试试看啊？还是你要问问题，还是要回答？好啊，请说啊。啊 ，x 属于 i。好。So you mean that okay, we change the word everywhere. A sequence of functions converges to G non-uniformly if for any epsilon there exists an M such that for any x in I, right? So this is in the right direction, but what you describe is just a good old definition of convergence, right? Or if we move 就是意思是说啊，这边这个 suggestion one, okay? For any epsilon greater than 我用白色哦 let me just use the white chalk. For any epsilon greater than 0, there exists M. 所以应该是 yeah, let's put and any x in I. Yeah, that's what you mean. Yeah, you can move this 这个子句啊 this description right here. For any epsilon greater than 0 and anywhere, any given x, any particular x, any one x in I, we can find M greater than 0 such that for any n greater than or equal to M, we have the function at that x minus the target, is it g? Yeah, gx smaller than s. But this is the definition for pointwise convergence. Okay, it's a broader definition. Okay, the pointwise convergence could be uniform or non-uniform. So if we want to specifically define what does it mean for convergence to be non-uniform, how do we modify the definition? That's my question. Yeah, 请说看啊。Right, yeah. Bigger than. 你上台写看好吗？我可以擦掉这些啊。So how would you modify the definition? Yeah. Give it a try. Now we talk about the convergence, the kind of convergence which satisfies this definition but does not satisfy that definition. That's the kind of convergence we are trying to describe. Okay, so let me try to read it. A sequence of function f converges to G non-uniformly if, let's try to see what's going on. If for any, 我想这应该是 for any 啊 ，no for some 这存在确实是存在啊。If there exists a non-zero epsilon such that for any given m, there exists some point in the interval such that the error there is greater than epsilon, however large. Yeah. 其实这个应该可以擦掉啊，差不多是这个意思啊。大家有没有感觉到啊 ？What does it mean for the sequence function to converge non-uniformly? That means this does not hold, or the stronger condition does not hold. So therefore, let me try to say, let me try to clear my mind. A sequence of functions converges non-uniformly to G if for some epsilon greater than 0, okay, and any given m, if for some epsilon greater than 0, however large m is, that means for any given m, we can find some x in the interval such that the error is greater than epsilon. Okay? So that's the definition of non-uniform convergence. That's a description of non-uniform convergence. So back in our context, thank you for your, yeah. Any comments right here? 谢谢两位同学啊。那 so back in our context, now let's try to clear our thought. So this is an example of non-uniform convergence because, let's say, because for epsilon, because there exists a small enough epsilon. Okay, so now the trick is consider, let's say, epsilon equals to delta divided by 2. So if this is the epsilon that we consider, then however big n is, you can always find an x in the interval, which is from minus pi to pi. Okay? You can always find a certain x at which the approximation error is greater than epsilon. And we know that we can always find a point. In this case, we can always find a point where the approximation error is about delta, which is greater than epsilon. And therefore, this is an example of non-uniform convergence. 大概是这样的感觉. All right? So for you to ponder mathematical fact, and I thank you both for providing insights. Okay, good insights. All right. So now, with that, I would like to move on to then how do we handle this? The ripple now cannot simply be suppressed. The maximum approximation error is not reduced by increasing n. Then what should we do? We need to start thinking outside the box. Okay? 我们就是可能要跳脱原来的思维去想象了啊。So now we need to, for the final 10 minutes, I want to tell you how to think outside the box. What box? Now we're designing a filter. Okay, so if we now look by what's going on right here, we design a filter by first looking at the ideal response, and we keep the middle part by truncation. Maybe we need to do something differently. We cannot simply keep the middle part, truncate, discard everything else, and then directly apply the filter. That's not good. That's not the best in terms of the maximum ripple right there. Okay, the ripple right there is delta is always going to be there. So can we try to do something differently? And the answer is yes. Let's try to multiply our ideal response instead of multiplying it with the rectangular window, which is right here. This is a rectangular window. Okay. Instead of multiplying with the rectangular, let's try to shape our response. Shape. 塑形一下 Let's try to shape our response by multiplication with some other window functions. So here on this slide, if you take a look, here on this slide, easy enough, we are showing 4 commonly used windows. Okay, what are they? Just in addition to rectangular, we have the Hamming window, solid line right here, the Hamming window, the Han window, which is the dashed line, 虚线的, that's a Han window right here. Just take a close look, and then we have the Blackman dashed dot line, 有一点一横的, that's a Blackman window which approach 0 even more smoothly than Han window. And then finally, if you will, you can try triangle. Try to just draw a straight line right here. Try to use a triangle. And the triangle window has a name right here. It's called Bartlett, okay, for your information. So these are the 4 different types of window in which you can use to multiply with the ideal response. Okay? The way we use these windows is still multiplication. Still, we multiply the window with our ideal response in the time domain. Still, that design principle is still there. Okay? And then we know that by multiplying the window, now the new windows with the response, we still have convolution in the frequency domain. And each window will still have main lobe and side lobe in their Fourier transform. But just the main lobe and side lobe now we have a freedom to choose in between different possibilities. So let's take a look at their main lobe and side lobes. Now, so here are a plot of the 5 windows. If we compare them, if you compare the Fourier transform, the magnitude spectra of each of the 5 windows, the rectangular right here, the Bartlett, okay, and the third to that, the third one is the Hahn window, fourth one is Hamming, and the last one is Blackman. Yeah. Okay, yeah. So first, let me tell you that these plots are in dB scale. Okay, yeah. Please note that these are not linear scale; these are dB scale. So we take the window transform, the absolute value, and take 20 log 10. Okay, yeah. 20 log 10. Therefore, these notches indicate the location of zero crossings. 掉下去的地方就是等于0了啊。This notches 掉下去的地方 notches correspond to the location of zero crossings. And here are all the 5 windows under the same n, okay? So you note that in dB scale, the main lobe and the side lobe, for the rectangular window, you can show that the main lobe side lobe difference here, if I remember correctly, that's around 13 dB, 13了. I've memorized that, 13 dB. That's the main lobe to the side lobe ratio, okay? 13 dB. And this ratio, we want to increase that ratio so that we have a better side lobe suppression. So you see that in Bartlett, the suppression is better than that. In Bartlett window, the suppression is more than 20 dB, so which is better than the rectangular window already. And then you go further to Hahn window, that suppression is around more than 30 dB, even better. The first side lobe has a height of smaller than what? Smaller than minus 30 dB. Even better. And then the Hamming window has this tricky property that it has a series of side lobes that the spectrum is almost flat. That's one thing to notice for the Hamming window. For the Hahn window, the spectrum has a nice roll-off rate, like that, straight line. If you see the envelope, 它那个包络 looks like the envelope 包络 looks like a straight line. Okay. And finally, the Blackman window has the best main lobe to side lobe suppression at more than, or should I say, about 60 dB, 60. Okay, compared to the rectangular window, which has barely a 13 dB suppression ratio. Okay, so Blackman has the best suppression, but to trade off, we exchange this performance with an increase in the width of main lobe. Okay. Note that the main lobe width is the widest for Blackman. 最宽的在这边 the widest for Blackman, followed by Hahn and Hamming. Hahn and Hamming is narrower than that, but yet wider than rectangular. Okay? Hahn, Hamming, and Bartlett, all 3 of them has the same main lobe width, which is double of the rectangular window. Okay? So you don't need to copy everything on your handout because the next slide gives you a summary. Okay? So we can almost end our discussion right here. So let's look at this table. Okay? Very nice table for you to be aware of. Okay? In your homework, you will also be using this table. Okay? So let's take a look. Take a look of the table. You have 5 different kinds of windows. And as I mentioned, the side lobe amplitude, peak side lobe amplitude relative to the main lobe is 13 dB, minus 13 dB for rectangular. And it increases, it gets better when we go down the table. Okay, this gets better when we go down the window. And corresponding to that, because as we mentioned, delta, what is delta? Delta is the total area for the side lobes, right? So you can imagine that the smaller side lobe we have, the smaller approximation we'll get in our design, right? So this one and that one, this column and that column is positively correlated. 它正相关的啊。有没有太快？会不会太快？ So we mentioned that this approximation error delta is the total area of the tail， 以8部分全部的面积嘛啊。So indeed you see that this also improved when we go down the table. Okay? Improve when we go down the table, but we are trading this property, this desired property, with the 一好没两好 with these two columns are trade-offs. Show you a trade-off. So we get better when we go up the table as we are talking about the width of the main lobe. The rectangular window has the most narrow main lobe. It's most narrow main lobe, and consequently, main lobe also tells you about the transition width. Okay, so the last two columns here, equivalent Kaiser window and the transition width of the equivalent Kaiser window. So we will talk about that next week. Okay, so please don't worry about the last two columns right here. In the next week, when we come back, we'll talk about there's another kind of window, a family of windows actually, called by the name Kaiser. Okay, Kaiser window, but so far we've seen. I suggest to you that there are different types of window for you to choose, and you can trade off so that we can trade off between the peak approximation error versus the width of main lobe, which dictates the transition width. Okay, transition width and the peak error there's a trade-off in between the two properties. Okay, so that's another information for today, and I want to quickly show you the homework. Okay, the homework, this homework, I want to ensure you that there will be the written part, which we discuss tomorrow, and can I increase this? Increase 放大一点. So there will be the written part, and please take a look. We'll come back tomorrow to discuss. And for the computer part, we will be looking at FIR design using MATLAB. Okay, so you'll be still use the same specification as last time: corner frequency, right there, DC gain, unity. And then the edge of stop band is set at 0.4 pi, and we require the gain to drop below 0.01. Remember that we've done this for IIR, right? In the last homework, we did it for IIR, but now let's try to work on FIR. So very similar specification, but I want to show you the code I created. So I've created a short code for you to play with. So in this code, still, we are going to apologize for everything looks small, but let me just run it. Okay. And this is the plot I want to point to you to bear with. So now you'll see that when you run the code, this is the IR, the Butterworth filter that we designed last time. And the magnitude response, we have this corner frequency 0.33, right? Pi divided by 3, pi over 3. That's the corner frequency, and this is the edge of the stop band. I require it to be smaller than minus 40 dB. This is minus 40. So I chose the order of Butterworth so that it dropped below minus 40 successfully. Okay, right there. But now, when I choose, you can play with the code. When you choose the order of your window, and in this case, I'm using the Han window. Okay, the Han window. You see that in this case, the transition width is too wide. Okay, transition is too wide from here to here. That's too wide. I want the stop band to start right here. So it does not satisfy the specification yet. So now it's your job to find a larger end so that this filter satisfies all the criteria. Okay, so that's the homework. And you will be designing, and this is a phase response. Okay, linear phase for FIR, non-linear phase for IIR. Okay, so hopefully you play with this code and tell me what you see. Okay, yeah. So see you tomorrow. Thank you for being here.